Hey there, in this lesson we're going to have to cover a little bit of theory. I know I told you we'll talk about the linked list data structure next, but I decided we should go over a few other things first. There is some math involved here, but don't worry, this is not a math course. I keep things completely practical, but you have to pay attention here since it's going to make you a better programmer. And you'll come across questions about some of these theoretical topics in interviews as well as algorithm discussions with colleagues in the workplace. Now, in computer science, a set of terminology has been developed to make it easier to talk about certain things. And you have to know what those terms mean. So hang on tight as I explain them to you right here in this lesson. Now, in order to solve any problem in computer science, generally we write computer programs. These are considered instructions, right? Instructions given to a computer to solve a particular problem. There's a term for this in computer science. The step-by-step code, those instructions we tell to a computer in a particular program is basically called an algorithm. Okay, so basically any piece of code that performs some operation can be considered an algorithm. And remember that in Java, everything happens inside of a method. And we can create all kinds of methods in which we provide instructions line by line on what exactly should happen. So let's take a look at a method. Here's some code that returns the count of even numbers in a list of integers. Take a minute to understand what's going on here. You should already know how this works if you have a little bit of coding experience. So in a nutshell, this method is supposed to return the count of how many even numbers there were in the input array. And these lines of code here inside of the method are instructions to the computer on how exactly to count the even numbers. And because an algorithm is simply instructions to a computer on how to solve a particular problem, the lines of code you see here can simply be referred to as an algorithm. An algorithm to count the number of even numbers in the given input. Now, we made this algorithm up to solve a particular problem, and I even made up this problem sort of on the fly here, but there are popular, well-known algorithms out there that are common in the industry, and we'll be learning about those pretty soon. I just want you to keep in mind that an algorithm is nothing but instructions to the computer on how to solve a particular problem, such as, sorting a list of items or searching for something in a collection of things. Some algorithms perform really slow, and others are more efficient. The one we have here performs reasonably well. Generally, an algorithm is considered efficient if it scales well relative to input. And for example, the one we have here will execute the loop as many times as a number of elements in the input array. So let's say we pass in an array containing 50 elements. The loop will run 50 times. Once for each slot of the array to check if the number is even or not. Now, if we have 100,000 elements in the array, then this loop will execute 100,000 times. So if we were to graph the efficiency of this algorithm, it would look something like this. The time it takes to run this algorithm is linearly dependent on the size of the input. In other words, this algorithm scales linearly as the size of input increases. So keep this terminology in mind. Algorithms that iterate an entire list of things once are typically linear. So if the array we pass to our method contains 10,000 elements, the loop would run 10,000 times. If the array we pass is 50,000 elements, the loop would run 50,000 times. Okay? So this algorithm is considered generally efficient. It's not super fast or anything, but it's acceptable. Now, are you ready to see the fastest algorithm ever? Take a look at this method definition. Okay, this only has a single line of instruction in the method body, and the method is called getElementFrom, and it accepts an array as well as the index position that we want to get the data from the integer array. So all it does is returns the data at the given index, and that's it. This is referred to as constant time, regardless of how large the input array is. It doesn't have to loop or anything. It just returns the element immediately. Okay, this is referred to as constant time. So just keep that in mind. Now take a look at how this looks on the graph. So notice the running time of a constant operation. regardless of the input size. We can have an array of 1,000,000 elements. It's going to run the same as an array that has just one element. It's just immediately going to return the data because we have the index position of where we want. So it's really not, you can't really consider it an algorithm, but it's really just an operation, right? Just a single line of code that executes once. That's what is meant by constant. So the running time does not get affected with constant operations. Only things that require a looping or recursion or some processing that takes place over and over and over again, those are the algorithms that take longer to run relative to the size of the input. Let's look at an algorithm that would be much slower than the one we have here. And that is a loop that's inside of a loop. And when we have loops inside of loops, things really start to slow down. For example, take a look at this method. This method is supposed to count the number of integers that exist in both of the arrays that are passed as input to this method. Items 1 and items 2 are the arrays. And the way it does this is by comparing each element in one array with every element in the other. So you can imagine that this kind of thing is not going to scale as well as the linear one we saw before. But then, of course, it solves a different kind of problem. All right. Now let's say if the first array contains 10 elements and the second array also contains 10 elements. That would result in 10 times 10, 100 iterations, right? Still not too bad, but if we have 100 elements in the first array and 100 elements in the second array, that jumps to 100 times 100, 10,000 operations. Now if the first array contains 1,000 elements and so does the second, we're talking about a whopping 1,000,000 operations, right? 1,000,000 iterations. So clearly this method is not as scalable as the previous one we looked at. The number of operations that will need to be run will be equal to the size of the input squared, okay? Take a moment to digest this sentence. The number of operations that will need to be run, or the number of iterations rather, that will be executed will equal to the size of the input squared. So if I was to graph the running time of this method, the graph would look roughly something like this. So as you can see, this does not scale as well with large inputs. The more input values we run in the algorithm, slower it's going to get. And this kind of a structure that has to iterate over a loop that is inside another loop is referred to as a quadratic. Okay, the term quadratic in math simply means squared. And the number of operations the computer will run in this kind of an algorithm is going to be the input squared. That's why it's referred to as a quadratic. So keep these terms in mind. We got linear, constant, and we have quadratic. And don't let these fancy mathematical terms scare you. I keep this course practical, so I promise with just a little bit more terminology and theory, we'll move on to writing some Java code. But it's important you understand how an algorithm scales with respect to the input size. And a way to communicate how an algorithm scales, computer programmers need terms like linear or quadratic to make it easier to talk about the efficiency of algorithms. For now, just remember that if there is a single loop that iterates over every single value in a given list, it's called a linear. It's going to be a linear algorithm. If there is a loop inside of a loop, then it's considered quadratic. Now, another term I want to introduce to you is called growth rate. And this simply means the way an algorithm scales as you give it more input. So you can refer to the single loop algorithm as a linear growth rate algorithm and a nested loop algorithm as a quadratic growth rate algorithm. Now, when we talk about terms like linear or quadratic, we're basically communicating in English. But to communicate these kinds of ideas globally, you need a language that transcends all countries and cultures, so there's no confusion. And in most sciences, this is done through symbols and notations, and computer science is no different. To communicate the efficiency of algorithms, we use a shorthand notation called asymptotic notation. Right? Now that may be a complex sounding word, but really it's quite simple once you understand. When we talk about an algorithm that scales linearly, we write this. And this is pronounced big O of n. A quadratic growth rate algorithm would be written like this, big O of n squared. And n here is considered the input size, right? The number of elements that were given to this algorithm to process. And this notation or equation, you can call it, represents the growth rate of the algorithm. In other words, how well this algorithm scales relative to the size of the input. How an algorithm scales relative to the size of the input. The key word here is the size of the input. That's all you really need to be concerned about at this point regarding asymptotic notation. Now let me ask you a pop quiz question. What do you think would be the asymptotic notation or big O notation for an operation that runs at constant time? Take a few seconds, think about it, and I'm about to show you right here on the screen what the big O notation for that will be. Here we have it. It's going to be big O of 1. Okay, there's just a single operation that's being carried out when it comes to constant, okay? Regardless of the input size, right? We don't even consider n. It's just going to be 1. One single operation, regardless of the input size, is the constant running time, okay? Now, what do you think would be the notation for an algorithm that has a loop that's inside of a loop that is again inside of another loop? So basically 3 loops in a nested structure. Take a minute to think about this, and instead of calling it a quadratic, this kind of an algorithm is going to be called something. Think about what that might be called. The notation for this is big O of n cubed, all right? And it's called a cubic growth rate algorithm. That's no surprise, right? And as you can imagine, this would scale even worse than a quadratic. If there are just 10 input elements for a cubic algorithm, the number of iterations would be 10 times 10 times 10. That's 1,000 iterations that would be needed. If there are just 100 input elements, we're looking at already a whopping 1 million iterations. All right, so things really slow down as the size of the input increases. Now, computer science could be pretty interesting. When you think of a computer, you get the idea that it's a pretty powerful piece of machinery. It could do a lot of things. It can solve a lot of problems. But there are a certain genre of problems that just don't have an efficient solution, right? An algorithm has not been discovered, and an efficient algorithm has not been discovered to solve those kinds of problems. Now, I showed you algorithms with 2 loops, 3 loops, but imagine if you didn't know the number of loops that were required to solve a particular problem. Right? Let's say if the input size was 10. Depending on the problem, we could just have a single loop, iterate over the whole thing once, and we're done. Or we can have 10,000 iterations or even 1 million iterations, 10 million iterations, depending on the kind of problem, right? For example, there's a problem called a matrix chain multiplication, and using a brute force approach to solving the problem, it takes an exponential amount of time. So, for example, an input size of just 10 would result in close to 10 million iterations. So these types of things really explode with the size of the input increasing, right? So just with an input size of 5 to 10, there's a massive, massive performance hit. And then from 10 onwards, it becomes almost practically impossible for a computer to solve unless we have an efficient algorithm in place. And there's a lot of problems out there that just don't have efficient algorithms. And an algorithm could just run forever and ever, for infinity, and just not be able to find the solution, right? And those types of algorithms have an exponential growth rate, all right? Where it's not squared, it's not cubic, it's actually exponential. The number of loops or checks required will increase exponentially relative to the size of the input, all right? By the way, the term complexity is often used in the place of growth rate or the scalability of algorithms. You can refer to these as complexities, big O of n complexity, or big O of n squared or n cubed complexity. So that's another term to keep in mind. You're going to probably hear it quite often when discussing the scalability of algorithms. Just understand that 3 loops in a nested structure, a loop inside of a loop inside of a loop, is a cubic growth rate or complexity. Nested loop, loop inside of a loop, is a quadratic growth rate or quadratic complexity. And one loop is typically just big O of n, which is a linear complexity. We've talked enough theory, so I think it's about time to start bringing this lesson to a close. Before that, though, let me just quickly summarize what we've covered so far in a nutshell. The topic of trying to figure out how an algorithm scales or how it performs, what's its efficiency, is referred to as the analysis of algorithms. When we analyze algorithms, we put them into these categories based on the number of steps or iterations that will be required for the computer to solve the problem. And the number of steps or iterations required typically depends on the size of the input. Some algorithms scale really well no matter how much input you give it, 1,000, 10,000, 100 million. Some algorithms perform just really well. Others slow down significantly as the input size increases. Now, in the beginning of the lesson, we started from a completely random algorithm that I made up that consisted of a single loop, and this falls in the linear category, which is considered pretty fast. With a nested loop, things get a bit slower, but still acceptable in most cases, and we can call it a quadratic. A cubic is often identified with a 3-loop nested structure where we have a loop inside of a loop that's again inside of another loop. Now, there are much faster algorithms to solve popular problems in computer science, and we'll be going through many popular, well-known algorithms in the course. Now, we are not completely through with algorithm analysis and big O notation. There's just a little bit more theory we need to talk about, another genre of problems that scale logarithmically. But I'll leave that for later. I know we've covered a lot of ground here, so there's enough for you to chew on. So in the next lesson, we're going to start to get practical, but I just want to let you know that we will be revisiting this for a brief period of time a little later on in the course. In the next lesson, we'll start to get practical and start coding in Java. So stay tuned, and I'll see you in the next lesson.